Hi guys! So I hope you had an awesome weekend. And just in case you have any questions on 12.1, there is a pen cast of the solutions up on School Loop, so you can check that out later. But hopefully you have some notes in front of you, and you're probably going to want to have a calculator handy because we're going to be multiplying some big numbers. So we are going to be looking at permutations, which actually you've already looked at, we just didn't call it permutations. A permutation is when you take a bunch of items or a bunch of options, like remember the UPS driver, and we looked at the different paths that he could take depending on how many stops he had. Well, that would be a permutation, where you are arranging things in a particular order. So even though he was going to all the same houses, each different path represented a different permutation. So that's what we're going to be looking at today. So we can go on down to how many permutations are possible of the letters A, B, and C. So even though it's the same three letters, we look at ABC is not considered the same thing as BAC or CAB. These are all three separate permutations. And so if we go through and we do like the trees that we did the other day, we can look at all the possibilities, and we already know from what we've already done that this is going to end up being 6 different possibilities, or 3 factorial, and that's because of the work we did the other day. So now we're going to take this idea of a permutation and extend it to bigger numbers, and what we talked about also, the truncated factorial. So these are called permutations without repetition. These are the first ones we're going to look at. So for instance, you have 8 people and they all enter a pie eating contest, and we want to know how many ways can a blue, red, and yellow ribbon be awarded. So we know that this is going to be an dependent event, because once somebody wins the first place or the blue ribbon, then that will take them out of our sample space and affect who gets the red, and that will then in turn affect who gets the yellow ribbon. So we already sort of looked at this as well. This is called 8 times 7 times 6. So we have filled the blue ribbon, the red ribbon, and the yellow ribbon possibilities, and we would just multiply those together. Now what's going to be different about this is, even though we call that a truncated factorial, and personally I would still just deal with it like 8 times 7 times 6 and do that on my calculator, we actually can come up with, you know how math is, we like to come up with formulas, and so there's another way of looking at a truncated factorial. So notice that if I took all 8 people and I wrote this out as my 8 factorial, and then below it, though, I know I only want those first 3 places. So if I divided by the places that I don't want, which in essence is the 5 factorial, I end up with my truncated factorial. So what's really happening here, though, is we have the 8 people that are in our sample space, and we are going to subtract from those 8 people the number of places we want to fill. So there were 3 places, blue, red, and yellow ribbon. So that's where that 3 came from. And that's what gave us the 8 factorial divided by 5 factorial. So we have a name for this, okay? Or we have a notation for this, I should say. So this is a permutation of n distinct objects. That was the 8 people in the contest, taken R at a time. So the R at a time means you have first the blue ribbon, then the red ribbon, then the yellow ribbon. So depending on your calculator, sometimes, and I don't want you actually to find this yet because I want you to know how to do it by hand, but you might see the NPR, National Public Radio, and or you might see it as an ordered pair. Realize it's not an ordered pair. P of n comma r is really just a way of representing this formula here. This is what's most important. So this is what we just did. This was our 8 factorial over 8 minus 3 factorial. Okay, so let's take a look at an example that we haven't done to see how this plays out. So we have a newspaper, has 9 reporters, and they are going to cover 4 different stories. So We have 4 stories that need to be covered by 9 reporters. So that means in the first story, we have a possibility of 9 different reporters. Once someone is chosen, now our sample space goes down. We only have 8 possible reporters, then 7, then 6. This is a truncated factorial. And in all practicality, that's all I would do, is just multiply those numbers together. But it also can be written as 9 permuted 4 different ways. Okay, so what does that mean? Or again, P 9 comma 4. So I want you to get used to the notation, how it will come to you. So this is going to be 9 factorial over 9 minus 4 factorial, which is 9 factorial over 5 factorial. Now you might think that that's a huge number and a real pain to have to multiply out, but what happens is if I start to write 9 times 8 times 7 times 6 times 5, as soon as I hit that number that is the same as the number down below, realize as I start to write this, everything from here on down is going to cancel with everything from here on down. And so, just like we were going to do in the beginning, you just have to multiply those numbers together, and you would end up with a lovely 3,024 different ways those 9 reporters could choose the 4 different stories. Okay? Okay, so now let's look at what happens when you have permutations with repetition. This most likely is going to happen when we're talking about permutating the letters in a word. So let's start off real simple. We have the word pop, like hop on pop. So when I start to rearrange these different letters, I don't know if you can see it on your paper, but I tried to, hopefully you can see it in the video, that one of the P's I left a different color to show that even though you have this ordering here, P-O-P, which looks the same as this ordering, the P's are in a different place, but it's still the same P, so it really counts as the same ordering. So if you ask how many different ways can POP rearrange, you guys might want to say 3 factorial, because we know there are 3 things, and we know that 3 things can be permuted 3 factorial ways. But when you're talking about repetition, such as the repetition of letters, what you have to do is divide by how many repetitions there are. So all these P's are getting counted twice. So since there are 2 P's, we're going to divide by 2 factorial. So what you really have here is 6 divided by 2, which is 3. So we really only have 3 unique permutations of that letter. So for instance, here I have the word C's. So that is 4 letters. So you might think 4 factorial, and we know that 4 factorial is 4 times 3 times 2 times 1, which is 24. But what you're going to have to do, I have 2 S's, so I'm going to divide by 2 factorial. I also have 2 E's, so I divide by another 2 factorial, and that leaves me with 24 divided by 4, which is 6. And what I have here are the 6 unique sort of rearrangements of that word. Okay, so putting it into a context, you have the number of permutations of n objects, those are the letters in your word, of which P and Q are alike. Those are how many repetitions are of that particular letter. So you just take, this is the total number in your word, the total number of letters, and then P, you might not have both P and Q, but this would be number of repetitions. Okay, so let's do a few. Banana, B-A-N-A-N-A. Okay, any Gwen Stefani fans out there? So we have 1, 2, 3, 4, 5, 6. So that means we're going to have 6 factorial. That would be how we could permutate those letters. But then I have 1, 2, 3 A's. So I'm going to divide by 3 factorial for the A's. And then I have 1, 2 N's. So I'm going to divide by 2 factorial for the N's. And then that's our only repetition. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. over 3 factorial, 3 times 2 times 1, so those are going to go away. And then we still have the 2 factorial, which is just 2. And so working that out, if you didn't have a calculator, 2 goes into 6 3 times. So 20 times 3 is going to give me 60. So there's 60 unique ways to rearrange the letters in banana. Hooey! Okay, then we have the queen of all words, Mississippi, Massissippi. Okay, so how many letters do we have there? If we count it out, we have 11. So that's going to be 11 factorial over, then we want to count all our repetitions. So let's see, I have 1, 2, 3, 4 i's, so I'm going to divide by 4 factorial for the i's. Then I have 1, 2, 3, 4 s's, so another 4 factorial for the s's. And then I have 1, 2 p's, so I'm going to divide by a 2 factorial for the p's. And if you were to go to your calculator and work that out, because I'm not going to do it by hand right now, you actually get 34,650 different ways to rearrange those letters. And that's smaller than if you were to allow for the repetition of the s's. So that's pretty huge. Okay, so now we're going to put this all together and do a few practice problems. So we're only focusing on permutations, the way you can rearrange something, sometimes with repetition, sometimes without. So initially I want you to know how to do it by hand, and then we will talk tomorrow about how you can do it on your calculator. I'm sure many of you will figure it out before then. So if I have p 5, 3, remember that that's going to mean 5 factorial, not over 3 factorial, it means over 5 minus 3 factorial. So that's going to give you 5 factorial, 5 times 4 times 3 times 2 times 1, over 2 factorial, 2 times 1, and then you just have to multiply the top. So 20 times 3 is 60. So if you have 6 factorial permutation of 6, 1, that's going to be your 6 factorial over, remember it's 6 minus 1 factorial, so that's actually going to be 5 factorial. So when you start this off, you have 6 times 5 over dot 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 over 5 dot dot dot. Those are going to cancel, and 6, 1 just equals 6. And then 6, 6, what does that mean? So that means we have a 6 factorial on top over 6 minus 6 factorial. Well, this is important because that means we need to standardize what does 0 factorial mean, and that's why I did this problem. So 0 factorial always means 1, because you can't divide by 0. Same way as we have anything raised to the 0 power is 1. It's more because it fits a pattern than because it has any actual value there. So 0 factorial represents 1. So when you see the two numbers here, it is just going to represent what 6 factorial would be, which is 720. So that just represents 6 times 5 times 4 times 3 times 2 times 1. Okay? All right. So try this for yourself. If you guys want to pause the video and try these next 3, that would be great. Otherwise, that's why I'm still talking. So I will go on and start to do these examples. The winner and first, second, and third runner-up in a contest with 10 finalists. So we have a winner and a first, second, third runner-up. So that's 4 different places that are being represented. So you have the winner, first place, second place, and then third place runner-up. So if we're going to do this, out of the 10 people, you have 10 possibilities, then 9, then 8, then 7. So really, you do not have to write this as a permutation, even though it is a truncated factorial. You can just write it as what we have here, and I'm going to need to do a quick, what is 720 times 7? Whoops, 720 times 7 is 5,040 is what you guys should get. 5,040. Okay, arrangement of the letters in the word parallel. So what goes on top? 1, 2. So that's going to be the number of letters in your word, which is 8. And then what do you divide by? So we look for repetition. We have 2 A's, so that'll be a 2 factorial. And then I have 3 L's, so that will be a 3 factorial. And so when you multiply this all together, you should get 3,360 different ways to rearrange the letters in the word parallel. And then lastly, we have an arrangement of 4 blue tiles, 2 red tiles, and 3 black tiles in a row. So 1, 2, 3, 4, 1, 2, 1, 2, 3. So if we're going to start with our blue tiles, we have a possibility of 4 times 3 times 2 times 1. Then we go to our red tiles, so there's a possibility of 2 times 1. And then we have our 3 black tiles. So we're going to do that one in green, which is going to be 3 times 2 times 1. So putting this all together, you have 4 factorial times 2 factorial times 3 factorial. And that's going to give you 24 times 2 is 48. 48 times 6 is 288 ways to rearrange those tiles in that way. Okay, so I hope this helps. And again, I've also done a pen cast of tonight's homework. You're basically looking at still independent, dependent, counting principle with some permutation. All right, good luck.